Okay, so I'd like to begin by thanking the conveners for inviting me to give this talk. So turbidite paleoseismology is an increasingly popular technique in which we take the frequency of turbidites that we see on the seafloor and we use this as a proxy for the frequency of earthquakes in the past. So I'm going to talk about a study that we did on the Sumatra margin where we compared the known history of major earthquakes with the evidence that we find for those earthquakes in turbidites in the stratigraphic record. And then this will lead me into thinking about actually in what settings are turbidites likely to provide a record of major earthquakes. So the basic idea of turbidite paleoseismology is that we have some earthquake at depth. This triggers a landslide or a series of landslides. These landslides evolve as they move down slope. They transform into turbidity currents that can then spread across the seafloor and deposit new layers of sediment on the seafloor. These layers build up over time, preserving a record of past turbidity currents and then presumably of past earthquakes. And in between, we hopefully have this background rain of sediment that contains datable material. And I guess the importance of turbidite paleoseismology is that it offers the opportunity to generate frequencies of earthquakes over much longer time periods than we know about, for example, from instrumental measurements or from historical records. And so we may get frequency of earthquakes over multiple earthquake cycles that we can then use in, for example, seismic modeling and inform things such as hazard prediction and mitigation. Now, I think it's important to point out that turbidite paleoseismology is underpinned by two assumptions. Firstly, every large earthquake produces a turbidite. If this isn't the case, then our record must be incomplete. Secondly, earthquake-triggered turbidites have special characteristics that enable them to be distinguished from turbidites triggered by other mechanisms. So we all know that turbidites aren't just triggered by earthquakes. They can, for example, be triggered by large storm systems, by direct fluvial discharge into the marine environment, or by random slope failures. In terms of special characteristics, this is usually taken as evidence of synchronous triggering of turbidity currents over a really widespread area that's unlikely to represent triggering by a different mechanism. So here's a bathymetric map of the Sumatra margin. In dark blue, we've got deep water and we have the trench. In red, we have shallow water. And then in green, we have the accretionary prism, which is characterized by these elongate trench-parallel slope basins. Now, the Sumatra margin offers a really good opportunity to test turbidite paleoseismology before applying it, because it's got this really well-characterized history of major earthquakes that extends back a couple of hundred years. And this includes two absolutely enormous earthquakes. In 2004, we have a magnitude 9.1, and in 2005, we have a magnitude 8.7. So what we can do is we can take this known history of major earthquakes and we can go and look at what is the evidence for these earthquakes as recorded by turbidites in the stratigraphic record, and indeed what is the distribution of those turbidites. Now, I think it's important to point out that if you want to apply turbidite paleoseismology, you need to use slightly different techniques to if you want to test turbidite paleoseismology. So if you're applying turbidite paleoseismology, you want a really long record that extends far back in time. So piston coring and gravity coring are ideal for that. But piston and gravity coring are violent coring techniques. They tend to damage or even destroy the superficial sediments, which are exactly the sediments that we want to capture when we're testing turbidite paleoseismology. So instead, we use multi-coring as an example of a multi-core on the right-hand side of the screen. So we get this, so it's a much gentler coring technique. We get this pristine sample of the seafloor sediments, and you can see at the top of the image, we even capture the seafloor, so the sediment-water interface. So this is the same bathymetric map, and now I'm showing you the locations that we collected our cores. And I think it's important to point out that we located our cores in places that you would reasonably expect to find turbidites. So turbidity currents are a type of gravity current. They're driven downslope by gravity, so they have a tendency to pond in topographic lows. So we chose deep points within slope basins. We also located some cores downstream from canyon mouths, and this is because this will be an area of flow expansion, and when flows are expanding, they're decelerating and likely to be depositing their sediment load. I'm just showing you here an example of one of our cores with its associated data. If you want to see more data, it's available in the paper at the bottom of the screen. So what you can see is we've got a photograph and corresponding log, and you can see from that photograph that we've got at least 30 centimeters of hemipelagic background sedimentation in there. There's some occasional oxidation bands in there. It's a bit bioturbated. There's certainly some bioturbated ash at the base of that core, which gives you that really high magnetic susceptibility spike shown in red. So we use C14 dating and lead-210 dating to get a handle on time within these cores. And so, for example, for this core, we can confidently say that no turbidites have been emplaced in at least the last 100 years. So we can take each of our cores from each of our core locations, and we can similarly look at the data and we can ask the question, are there turbidites that could have resulted from the earthquakes in 2004 and 2005? And I'm just going to put a tick in the location of a core if the answer to that question is yes, and a cross if the answer to that question is no. And so what you can see in this image is that within the slope basins, we find no evidence of turbidites that relate in age to these known large earthquakes in 2004 and 2005. Now, the situation in the trench is a little bit different, and part of that results from the fact that we have problems dating in the trench. We're below the carbonate compensation depth, we can't use C14 dating, and lead-210 dating is very tricky down there, but it is fair to say that we do find more turbidites in the trench than we find in slope basins. In fact, we find a very different record in the trench to on the slope. So we can also ask the question, are there turbidites that could have resulted from historical earthquakes? And actually we see a very similar trend, so we see very few So we see no turbidites in most of our slope basins that could relate in age to these historical earthquakes. There's an exception in the north where we have one basin which contains some turbidites that might relate in age to those earthquakes. And actually the situation in the trench, once again, is somewhat equivocal. So I think it's important to point out at this stage that this is not the only study that has tried to compare the historical record of earthquakes with the evidence for those earthquakes in the stratigraphic record. And it's not uncommon for other studies to find evidence for some, but importantly not all, of the known earthquakes. So turbidite paleoseismology is underpinned by these two assumptions, that every large earthquake, firstly, every large earthquake produces a turbidite. And based on the evidence that we have, or based on our data from the Sumatra margin, we actually don't find evidence that this is the case. It's somewhat difficult for us to answer the second question because we find so little evidence, so few turbidites on the margin, and the turbidites that we do find aren't really correlatable from one place to another. So I think it's quite important at this stage that we don't actually throw the proverbial baby out with the bathwater and hold our hands in the air and go, oh my God, turbidite paleoseismology does not work. Instead, I think we need to proceed with caution and actually start thinking about actually what are the characteristics that may predispose a margin to being more or less suitable for applying turbidite paleoseismology. And so I think margin morphology must be pretty important. So there's two pieces of bathymetry on the screen. At the top, this is just a little chunk of the central Sumatra margin. At the bottom, I've arbitrarily chosen a bit of bathymetry from offshore San Francisco. And my point is that these two pieces of bathymetry, these two margins, are very different to one another. So in Sumatra, actually we find no through-going canyon and channel systems that can connect the slope into the deep sea, whereas, for example, offshore San Francisco, we do. So we can start to ask questions like, actually, are canyons and channels, are they good or bad for turbidite paleoseismology? And they might be very good because they might actually help your initial landslides to transform into turbidity currents, and they certainly mean that your deposits will tend to end up in the same locations at the mouth of your canyons. On the flip side, they may also help flows triggered by other mechanisms that we don't want to collect to get to the same locations. The interplay of sedimentation rates with earthquake frequency and magnitude must also be important. So if we have a high sedimentation rate, then we're going to predispose a slope towards failure in the event of an earthquake. And we're going to replenish those slopes with new sediment in between earthquakes. So you'd think that if we have a high sedimentation rate and we have infrequent but large earthquakes, then we're more likely to get a good record of those earthquakes than if we have, for example, a low sedimentation rate and a high frequency of earthquakes. So sedimentation rate, the frequency of earthquakes, the magnitude of earthquakes, I think the nature of ground motion and margin morphology must all be very important in determining what settings do we actually produce a record of major earthquakes. But I think if we want to understand the interplay between these different parameters, then we really need more studies like this one in Sumatra in locations where we can compare the marine stratigraphic record with the historical earthquake record. So in conclusion, turbidite paleoseismology is underpinned by the assumption that all large earthquakes generate turbidity currents synchronously and over a large area. In slope basins on the Sumatran margin, we find no evidence of turbidites that correlate in age with the earthquakes in 2004 and 2005. And we found a similar result for turbidites related to historical earthquakes. So I think in order to understand where and how to apply turbidite paleoseismology, we need more studies in locations where the marine stratigraphic record can be compared with the known history of major earthquakes. Thank you.
We do have time for questions.
Yep, hello.
So I have to disagree. I think the rationale for turbidite paleoseismology rarely or perhaps never includes those first two assumptions. Those are not part of the rationale for turbidite paleoseismology. Those are the hypotheses that you're testing. That's not an assumption. Grand Canyon difference between an assumption and a hypothesis. And second of all, Jay Patton, who's sitting right over there, has a paper with, I think, 11 or 12 turbidites in the 2004 rupture area that have abundant evidence of the 2004 turbidite.
So I think there's 2 points there. So the first point was, what was the first point? Was assumptions versus hypotheses. So if I understand correctly, what you're saying is that in order to get a complete record of earthquakes, you don't need all earthquakes to generate turbidites, which I would disagree with.
That's correct. So a turbidite record, at the very best, can only give you a minimum frequency.
Okay, so then I think you have to start thinking about how valuable is that record. So you need some idea of how many earthquakes you're actually capturing. So I guess on the second point, it's very nice of you to bring up the fact that there's a lot more cores have been collected along this margin. But my understanding of Jay's paper is that he published 15 of those cores out of a possible 109 cores. And of those 15, 3 of them showed evidence of turbidites that related in age to those earthquakes in 2004 and 2005. So I guess I would disagree, and I'd encourage you to actually publish the rest of the data set.